Our next technique are greedy algorithms. Let's say that we have a graph of solutions. These peaks are what we call optimums. Some are local optima, but obviously there is one best solution, the global optimum. The greedy approach attempts to locate a local optimum as fast as possible. So let's say that we started here, and we got this initial solution. A greedy approach or algorithm would want to quickly improve upon that initial solution to get a local optimum. So the basic idea is, take what you can get now. If the global optimum is not required, then simple and fast greedy algorithms provide good enough solutions. Let's have an example. I'm sure you still remember the minimum spanning tree problem. Here we find the minimum possible number of edges where each vertex is connected, and that the sum of all the edge weights is minimum without forming a cycle. There's two popular greedy algorithms for this, namely Kruskal's and Prim's. For Kruskal's, you always get the shortest edge. For Prim's, you get the nearest neighbor. Let's try Kruskal's. So we take the smallest edge first, AB, and then maybe BC, and then FG, and then CE. Next is FA. So can you imagine the tree? Then finally, CD. Because there's no other edge that is small enough that won't form a cycle. So we got this one and this one as our minimum spanning tree. For prims, we start at a certain vertex, let's say A, and then we pick the nearest neighbor. So starting at A, we go then to B, then to C, and then to E, and then A to F, and then F to G, and then finally C to D. Both algorithms found the same MST. Even though they're greedy algorithms, Kruskal's and Prim's, they guarantee optimal MSTs. Let's have another problem. The traveling salesman problem. Let's first define the following. Hamiltonian cycle. It is a cycle that includes all the vertices of the graph. The traveling salesman problem wants to find a Hamiltonian cycle whose sum of edge weights is the minimum. It's also stated like this. Given n cities, find the shortest round-trip route connecting them all with no city visited twice. Here are some greedy algorithms. Modified Kruskal's. Shortest edge, but no new edge should form a cycle except for the last edge. Modified Prim's. Nearest neighbor, but no new edge should cause a vertex to have a degree of more than 2. Let's try both on this graph. If we use modified Kruskal's, we'll get AB, and then BD, then DC, and then unfortunately we'll have to get CA. If we're going to use Prim's, and let's start with A, we'll have to go to B, and then D, and then C, and then unfortunately we have to take this edge as well. As you have noticed, our algorithms didn't find the optimal solution. So greedy algorithms won't find the optimal TSP tour for this graph. So greedy algorithms are fast, but obviously do not guarantee optimal solutions. A technique that does is called backtracking, which we'll discuss next time.